Hi guys, I'm back with another arcade PCB repair, another step-by-step troubleshooting and repair of you guessed it, it's another Double Dragon. It has actually been a while since I did my last video, and that is because I actually moved to a new house, but the good thing about that is that I now really have plenty of room for my arcade PCB repair equipment and for all the stuff that I'm needing at that. I don't have to do any more repairs on the floor actually. This board has a graphics problem, that's all that I know so far. I already took a look at its physical condition and saw that it's actually in quite good shape, no corrosion on it, no obvious damage. It's a pretty clean board. So I thought that we'd actually hook it up and power it up to see what the board does. Some people have actually been asking me what's it with all those Double Dragon PCBs that you have been showing videos about. So because this is I think the fourth Double Dragon repair video that I do, or maybe even the fifth. Well, first of all, this arcade game is actually one of my favorite games, and I've come across a lot of non-working boards, and I've probably made about a dozen repairs by now, and I'm so familiar with the board that it's actually pretty convenient for me to do those kind of repairs, and I simply can't resist if I see a non-working Double Dragon board to get it back to life. Some people have been complaining that it's too much Double Dragon and that I should also repair some more other boards. Some actually told me that they like it because if maybe this topic, the Double Dragon, has been covered really deeply and in depth, then most people will be able at some point to repair their boards, whatever problem they might have with it. But I can assure you that other PCB repairs are coming up. I got a non-working Centipede Atari Classic arcade game PCB which is non-working, and I got a Roadrunner PCB which is an Atari System 1 game which is not working also, which will probably be up next. Okay, but now let's get to the Double Dragon. Okay, so let's fire up the board. Okay, this is what we get. So the game is running actually. This is the title screen. But if you're familiar with the game, you notice that the dragons are missing in the background. And this is, okay, screen which is all gray. Funny. But we have the text overlays, like the score, the time, and the player symbols and the credits. And maybe the sound. Okay, the sound is working also. Okay, so there's the high score table. So as you might already know from my previous videos, when it comes to the graphics that are displayed on the screen, you do have several layers of graphical data which are mixed together to actually get the final picture that you see on the screen. And that is true for most arcade games. So most arcade games have some sort of a background layer. That would be where in Double Dragon you can see the buildings and the street. And you would have some sort of sprite layer. That's the player's characters and the opponents. And on top of that you would normally have, like you see here, the text layer, which displays the score and credit count, etc. So what we are seeing here is actually probably just the text layer, and the objects and the background are gone. Well, the background is gray and there's no objects to see. So we should actually be trying to look at what is wrong with those two layers. So I think we'll start to poke around with the logic probe, maybe after taking a short look at the schematics to check where to start. Okay, so what would be a good place to look at the schematics? That would be the next question. And I think in the Double Dragon schematics, this page right here would be a good place to start. We actually came across this page before in an earlier Double Dragon repair, and I'll post a link in the description below, so you can check out that other video if you like. At this particular spot in the schematics, there's actually a selection taking place, and there's graphical data coming in from the background layer, down here, from the object layer and the text layer, the text overlay layer, and all this data is coming in through those buses here, and there's a certain prompt chip over here which is actually selecting through these lines here, A and B on these multiplexers. This prompt chip is actually selecting which graphical data is actually being displayed for a certain pixel on the screen. Will it display the background, or will it display the object that might be on top of it, or will it maybe display the text that might be even be above that? And this prompt chip actually is hooked up to those data buses also, like those multiplexers. And for instance, as you can see here, these are all the input lines of the PROM. You can see that the first 4 bits are coming this way down here, are coming from the background layer. So it checks the lower 4 bits of the background layer. Then it mixes 4 bits together in this gate. These 4 bits are coming from the text layer. This is another input to the PROM. And then there's 4 other bits going into this gate, and they all together also form this NOR gate. They form an input to the PROM. The line, the bit number 7 of the object data line is going in as a separate input, and the data line number 7 from the background layer is also going to the PROM as a separate input. And with these inputs, with this data that the PROM is getting, it is actually making the decision which layer to display at a certain pixel on the screen. And it is doing that by outputting those 2 bits. With those 2 bits you get 4 possible combinations. You only need 3 because there's only 3 layers, so only 3 combinations are used. But with those 2 bits, the prompt chip is actually selecting the layers by addressing those multiplexers A and B inputs. Okay, on the PCB we got the prompt chip right here, and the multiplexers that it is controlling are those 4 over here actually. and they got the A and B inputs to select between 4 possible input lines, and they are on pins 14, which is A, and on pin 2, on pins 2, which is B. So on 14 we got A, and A is stuck high. Well, yeah, it seems to be stuck high. And on B, which is pin 2, seems to be toggling. But 14, 14 is stuck, so this can't be right, really. It can only, if one bit is stuck, it can only be switching between 2 layers and not 3, actually. So what would that mean? If A, which is the lower significant bit, would be high all the time, then it could actually only switch between layers 1 and layer 3. And if we look here, M coil would be layer 1, and layer 3 would be B coil. So it can actually only show background. It is switching between background and text layer, and it's never displaying objects. So looking at the screen, we can confirm that, but well, it's not really showing any nice background either. So maybe something is also wrong with the data that is actually coming through those graphical buses. So maybe as a next step, we could look at the input pins of the PROM and at the data bits of the different graphical channels. So maybe it's not really a problem of the PROM not generating the correct output, but maybe it is not getting any nice input in the first place. So that would be the next thing to check. Okay, so probing around on the input pins of the PROM actually showed that there's something going wrong with the B-coil signal, because most of its lines are mostly stuck high. Several bits are stuck, some are moving sometimes, but it's not happening much at all. So I think there's a problem with the B-coil signal lines. So in the schematics, we would now try to trace back the B-coil signal and see where the problem lies. Those two inputs, 2 and 3, which are coming from the object and the text layer through those NOR gates, seem to be working fine. We can check them again. So lines 2 and 3 are actually toggling. They are working okay, but the B-coil signals input lines seem to be mostly stuck. So let's take a look where the B-coil signal is coming from. Okay, and generally speaking, at this point in this repair, we can be happy to say that we're most likely to succeed, because we already have a major clue. We already have found some signal lines that are carrying signals that cannot be correct. We don't really know what particular component might be malfunctioning and causing the incorrect signals, but that's not a big deal, because we can actually trace the signal back through the schematics. That's what you always do. If you find something, some signals that are wrong, you always trace them back through the schematics you see, and you check where those signals are being generated. And if you're going one step back, another step back, another step back, you'll eventually come to the faulty component. So we are tracing the trail of blood that leads to the murderer, so to speak. and we should be successful. Okay, so looking at the schematics, we can see that the B-coil signal is actually coming from the lower PCB, from the graphics PCB. And checking through the schematics, I actually got pretty confused at first, because somehow the signal is being renamed after it switches PCBs. So the signal that we are that we want to be looking at is this one right here. It's called BCG over here. And I already checked some of the ICs, and I have checked those flip-flops down here. You can see that those are outputting the BCG signal, bits 0s through 7, and the outputs are stuck high, but the inputs are also stuck high, so there shouldn't be anything wrong with this one. And I checked this flip-flop. The outputs are stuck high, but the inputs were stuck high also, so this guy over here isn't suspicious as well, but the signal is over here coming from this chip right here, which is a RAM chip. And the outputs of this RAM chip are, every single one of them is stuck high. So the data lines of the RAM chip are stuck high. So this can't be right either. So the next thing to do would be to check the address lines of the RAM chip and the output enable and write enable signals of the RAM chip, to see if the RAM chip is doing its job, or maybe if there's a problem with this RAM chip. Okay, and this is the RAM chip in question over here. It looks a bit dirty. And if we look at the address lines, like these for instance, pins 1, 2, 3, they are toggling all the time, so the addressing seems to be alright. Next thing to look at would be the output enable. So is anyone telling this RAM chip to actually output something? And that would be pin 20. So this is 24, 3, 2, 1, 0. This is pin 20. So this is low. And the output enable is an active low signal. So this RAM is supposed to output something most of the time. I say most of the time because if we wait a second, there you could just see it. Sometimes it appears to be toggling for a short moment. Mostly this RAM is actually supposed to output data. But there's some, like here, you could just see it. Sometimes there's something else going on. And if we look at the write enable signal, we can, this is pin 21 next to it. This is mostly high, meaning that the RAM chip is not written, but sometimes it's toggling also and it's going low. So what you can see is that those lines are actually appear to be working, and the way the chip is used in this under those circumstances here is that very rarely there's something written to the chip, but there's mostly something read from the chip. And if we now look at one of the data lines, which would be pin 11 for instance, we can see that it is mostly high, but intermittently it should also, there you could see it's also toggling. And I guess this is, well, right in the moments when the chip is written, there's actually some data being sent to this RAM chip other than just ones or just high signals, which can be seen here intermittently. So all of this leads me to believe that this RAM chip is actually bad. So I guess we should actually remove this chip, put a socket in, and put a replacement RAM chip in and see if we get any better. Okay, just before replacing the RAM chip, I just thought, could there be actually more than one problem with this PCB? Because even if the background channel is the background data channel is failing because it only is carrying high signals, would that actually lead to this situation where the objects on the screen are also missing, or is there maybe another problem with the objects, so the player and sprites and opponent sprites as well? And I actually did a little test on the PROM chip over here. I actually removed one of the input legs of the PROM chip, which was stuck high all the time because the background color signal was stuck high all the time. And I did a little something which actually showed me that the objects are right. So well, now as you see nothing at all. But if I, for instance, connect a wire to this input pin of this PROM, and I then connect the other end to ground, for instance, over here, then we can see that the objects are actually there. So what did I do there, and how did this work? You should actually see on the title screen the dragon. Yes, there it is. Well, I actually changed the incorrect background signal from high to low on one of the bits, which is bit 7, and that actually accidentally or whatever led to the PROM to decide to display the sprites again. So I think if we fix the B-coil signal, we should actually be fine, and we should at the same moment be getting our sprites back. Oh, and by the way, I actually think the purpose of this RAM chip on this board, judging from the schematics, should be to actually store the background tiles that are displayed on the current screen. So the background graphics are made up of tiles which I think are 8 by 8 pixels, and this RAM chip is storing all the tiles for one screen. And you can actually see that if the screen is scrolling, so if the background is moving, the tiles have to be rearranged and shifted over. This is actually the moment when the write enabled signal on this chip is being pulled low. And also if the game is switching from the in-game graphics to the title screen, you can actually see that the write enabled signal on this chip is wiggling. So this chip is actually storing the background graphic tiles for the current screen. Okay, so I removed the RAM chip and I put a socket in. And also very interesting, if you are having a suspicious component and you are removing it from the board and wanting to replace it, of course, but if you fire up the game without the component after having it removed, like the RAM chip in this case, and the game looks actually the same, this pretty much tells you that this RAM chip well, didn't probably do much with the game. So that's first good sign. I will try to find now a working RAM chip in my storage, and we will try if the game is getting back to normal with that. Okay, so I have a replacement chip right here. So Let's plug it in. As you know, I always like to do this while the game is running, because it makes some nice colorful effects on the screen at times. Like this. Okay. Ha. So we got something. It's not looking right, but it's looking right now, because when I put the chip in, it wasn't containing any particularly good data, of course, and but with the next change of the screen it was probably written, and so now if the game switches back it should be fine. Yeah, and here we go. Another Double Dragon back from the dead, with just this one chip needing to be replaced. Otherwise a really nice and clean board. Okay guys, so thank you again very much for watching this video. If you liked it, please subscribe. You are free to watch, of course, all my other arcade repair videos, the Double Dragon videos and the other videos that I uploaded. Stay tuned for some more arcade related videos, and especially arcade repair videos that I'm going to be posting. Okay, so see you soon.